Okay, we're going to start off by going over the exit ticket from last class. So this was our first introduction with probability rules. So we talked about unions and complements for the most part and sample spaces. All right, so number one, a fair die, meaning like equally likely outcomes, with its faces numbered from 1 to 6 will be rolled. Which of the following is the best interpretation of the probability that the number landing will fit the number landing face up will be less than 3? All right, well, first of all, each outcome is equal to 1 over 6, right? Rolling a 1 has a probability of 1 over 6. Rolling a 2 has a probability of 1 over 6. 3. Shouldn't try and write too fast or my brain gets ahead of my hand. All right. All right, so here are my 6 outcomes, right? The probability that the number landing face up will be less than 3. Well, 1 is less than 3 and 2 is less than 3. I can't include 3 because 3 is equal to 3, not less than, right? So I ended up having 2 out of 6, so my probability is 2 out of 6, which can be reduced to 1 over 3. All right, so automatically I can eliminate B and C because they have 1 over 2 and 2 over 3. D, for 3 rolls of the die, a number less than 3 will land face up 1 time. It will take 3 rolls of the die before a number less than 3 lands for the first time. Or A, for many rolls of the die, the long run relative frequency of the number less than 3 landing face up is 1 over 3. So A is our answer here because probability is always a long run relative frequency. So long run means long term, right? So over many, many, many rolls of the die. And then relative frequency is our same thing as probability / percentage. So long run relative frequency is what probability is over the very long term, right? So these two are trying to predict the short-term future, and we can't do that. We can't predict the short term. We can say over the long run, the probability is this much, 1 over 3. All right? Number 2. High school science teacher has 78 students. Of those, 35 are in the band. So let's see, 78 total, right? Of these, 35 are in the band and 32 are on a sports team. There are 16 students who are not in a band or on a sports team. One student from the 78 will be selected at random. Let event B represent, let me get my highlighter. All right, we're going to have B represent selecting a student in the band. And then we're going to let S represent selecting a student on the sports team. Are B and S mutually exclusive? All right, so that term mutually exclusive means they cannot happen at the same time. Cannot happen at the same time. All right. So technically, you can be in the band on a sport and on the sports team, right? So let's see if these students are actually on the band and in the band and on the sports team. What I'm going to do is I'm going to sum up these breakouts and see if they equal 78. If it equals 78 exactly, then I know that I have band, sports, neither, and those are my 3 separate groups. And they would add up to the total. $35 plus 32 plus 16 gives me 83. My total should be 78. So it looks like I have 5 students overlapping. There's 5 students in more than one group, right? And it can't be the neither group because the neither group is by itself. It's in neither band or sports. So that means I have 5 students who are in both of these groups right here. They're in the band and they're in the sports because we're double counting them, right? So what that means is, no, they're not mutually exclusive because there's 5 students that are in both. So let me go ahead and eliminate D and E because those say yes. Now let's look at the explanation. This says no because the probability of B intersection S. That's intersection. You should be thinking of the word and. Intersection and. Remember, intersection is the part of the Venn diagram where the 2 overlap, right? So that's the intersection. So what that means is since 5 students are in both, my intersection is 5 out of those 78 students, right? So A is my correct answer here. Because the intersection, what we've double counted that's in both groups, is 5 out of 78. All right? Next up, number 3. At a sporting event, cheerleaders will throw 50 bundled t-shirts into the crowd. The t-shirt sizes consist of 10 small, 15 medium, and the remainder either large or extra large. Suppose Anna catches a t-shirt. What is the probability that she will catch a t-shirt that is not a size small? So when we see that not a size small, I hope you guys are thinking complement. So this is the probability of an event not happening, right? I'm going to call this event S. So to get the probability of event S complement, or the size small not occurring, we need to do 1 minus the probability of getting a size small, which I think we know, right? The probability of getting a size small is going to be 10 t-shirts over my total, which is 50. (10 divided by 50 is going to give me 0.2. So I know I'm going to have 1 minus 0.2. All right. 1 minus 0.2 is going to give me 0.8, which is answer choice E. That's my probability of not getting a size small, 80%. All right. Last up. As a promotion, the first 50 customers who entered a certain store in a mall were asked to choose from one of 2 discounts. First discount was 20% off all purchases made that day. Second discount was 10% off all purchases for the week. Of those who received the discount, 28 chose the first discount, 22 chose the second. One customer will be selected at random. Let F represent the first discount. And let S represent the second discount. Are F and S mutually exclusive? All right, that means can F and S happen at the same time? Well, let's check it out. First, we need to calculate the probability of F and the probability of S. All right, so I know that I have 50 customers total, so that's going to be my denominator for both of these calculations. I have 50 total, right? The first discount of those who received 28 chose the first discount. Let me highlight that right there. So I know that's got to be my numerator for P of F. And then 22 shows the second discount. So that's going to be my denominator here. All right, so if I'm converting it into decimals, I get 0.56, and I get 0.44. If I add these two together, I get exactly 1, right? So what that means is that there's not anyone that's in the first group and the second group together. I didn't double count anybody, right? 28 plus 22 gives me 50. That accounts for all 50 customers. There's no one that's in both of the groups. So yes, they are mutually exclusive. So I can go ahead and eliminate this and this because I haven't double counted anybody, right? There's 28 in the first group, 22 in the second. So let's look at the reasoning here. All right. Yes, because F intersection S is 0, F intersection S is 0.12, and F intersection S is 1. Well, at first, C looks like it's likely because when I added them up, I got 1, right? But that's not actually what this is saying, right? This would be correct if it were F union S. That's because F plus S would equal 1 if it were a union, but that's not what this symbol means. This symbol means intersection. And what intersection means is and. So if I have two mutually exclusive events, they never intersect. Remember, the Venn diagrams are like two circles next to each other. They never intersect. So I don't actually have an intersection, which means A would be my answer. Yes, they're mutually exclusive because F intersection S is 0, meaning that there is no intersection. So that's why you have to be careful with the notation. I want to go ahead and fill out this graphic organizer at the back of that packet 3 of all the probability rules that we've learned, like all the different ways that we can approach probability. All right, so first off, I could just have an event in a sample space. That's the very first thing we talked about, right? Sample spaces. So we could have an event that has more than one equally likely outcome. So that's when we talk about the spinners, right? Example. Spinning a spinner twice. Remember my example where I could have red, 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 blue, red, yellow, blue, 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 red, blue, yellow, 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 red, yellow, blue. So that's my sample space, right? My total outcomes is equal to 9, and then each event, I would divide it by 9, right? The 9 would be in the denominator. Whatever I'm looking for, I would count it, and that would be in my numerator. So this is a sample space. So I could do that. If I'm given a scenario where I can easily write out a sample space like this and then just circle, like for instance, if I'm looking for a probability of red, I could just circle the red. And then do 5 out of 9. So that's something that I would approach first. If you can easily create a sample space with equally likely outcomes, then just set up a fraction. All right, you've also got if an event occurs at least once. So that's the same scenario over, just create a sample space. And then number 2, circle outcomes where event happens at least once. And then number of outcomes in event over the total. So remember, probability really is just a fraction. We just got to figure out what to put on the top and the bottom. All right, so these two were basically kind of the same thing, right? Except maybe in here I could talk about, instead of 2 events happening, I could have like flipping heads or flipping tails, that kind of thing. So these two, you're creating a sample space and then circling all the events that are considered part of the outcome. I'm sorry, circling all the outcomes that are considered part of the event. All right, if an event has more than one outcome, that's not equally likely, right? So if you have an event, let's just say I could have, probably should have had an example already. All right, let's say I didn't have a fair coin, right? Let's say that heads was 60%, 0.6, and tails was 40%. So what if I flip it twice? What are my outcomes? Well, I still have a sample space, right? But they're just not equally likely. So I would have heads, tails. I would have tails, heads, 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 and tails, tails. So you'll notice that I still created the sample space. That's what this whole square is about. If we have an event in a sample space, we can create the sample space. But here's the trick. I'm actually going to use the multiplication rule to figure out the probabilities here. So rolling a heads then a tails is going to be 0.6 times 0.4, right? So the probability of this outcome is 0.24. Same with tails heads. I'm going to do 0.4 times 0.6 and I'll get 0.24. Heads would be 0.6 times 0.6, which would give me 0.36. And then tails would give me 0.16. So I still have a sample space, they're just not all equally likely like I have up here. Here I had 9 options that were equally likely. Down here I have to actually state out the probabilities and I have to calculate them because they're not equally likely. So rolling a heads then a tails, I had to multiply because I had my AND rule. If you'll notice something, once I have the sample space set up, all the probabilities should add up to 0. And that, I'm not add up to 0, you guys know what I meant, add up to 1. Alright, so now that I got my sample space, we could say, what's the probability of rolling tails? And I would say 0.16. What's the probability of rolling at least 1 heads? Well then, at least 1 heads I would do here, here, and here, and I would add up these numbers. The probability of rolling at least 1 tails, I would add up this number, and this number. So once you have your sample space, you're able to calculate different scenarios. So I would definitely try and create a sample space first, if the problem will allow for that. All right, we've also talked about complements. So remember, let's say the probability of event A, if we're looking for the probability of A complement, it's equal to 1 minus the probability of A. Basically, with the sample spaces, all of your probabilities are adding up to 1, right? So here you've got 2 scenarios. You've got event A happening or not happening, right? It's either going to happen or not happen, so they have to sum up to 1. That's why it's 1 minus the probability of A. That's our general complement rule. All right, at least 1 success in a series of independent events with the same probability of success. So that's like the duck hunt example from today's class. So it's basically a complement rule, and I'm going to show you how. So say we are free throw shooting. And our percentage is 0.68. So that's our free throw percentage. Say we're going to throw 10 in a row, 10 free throws in a row. What's our probability of hitting at least 1? Well, if you think about it, what's the complement of hitting at least 1? The complement of that is hitting none at all. So I can set this up as a big complement rule by saying the probability of hitting at least 1 free throw is going to equal 1 minus the probability of hitting, if I could spell the word hitting, 0 free throws. Those 2 scenarios have to add up to 1. You're either going to hit at least 1 or 2, 3, 4, 5, 6, that all falls in here. If you hit 7 free throws, that falls in this scenario. If you hit all 10 free throws, it falls in this scenario. The only thing that doesn't fall in this scenario is hitting 0 free throws. So the only tricky part is figuring how to calculate this, but we also learned how to do that today with our intersection multiplication rule, right? So we would take our complement here, 1 minus 0.68. So if our probability of hitting the free throw is 0.68, our probability of not hitting it is 0.32. That's how a complement rule works. So if I were not going to hit the free throw 10 times in a row, it would be 0.32 to the 10th power. Remember, if I have 10 times in a row, I'm going to multiply it 10 times in a row, which is the same thing as saying an exponent of 10. So let me go ahead and put this into Desmos. No, I don't want that. There we go. My phone's cracked, so it's hard to see. All right, so my probability of hitting at least one free throw is going to be 0.999887. Now let's just do a reasonableness check on that. Does that make sense that my probability is so high? Yes, I have a pretty good free throw percentage. I'm going to hit it 68% of the time. So if I'm throwing 10 free throws, I'm probably going to hit at least one of them, right? So remember, that's a form of the complement rule because I would do 1 minus the probability of hitting no free throws at all. All right, now we've got our union and our intersection, and we have 2 scenarios with each. So with unions and intersections, I think it's the easiest to draw a Venn diagram if we can. So with mutually exclusive, our 2 circles are not touching at all. Let's call this event A and this event B. So the probability of A union B is going to equal P of A plus P of B. I don't need to subtract anything out because I haven't double counted anything. So that means the probability of A intersection B is 0. They don't intersect at all. All right. Now, the probability of non-mutually exclusive events. So here, they can happen at the same time. So I've got A here, I've got B here, and then this is my intersection. We have basically the same formula here. The probability of A union B, I'm still adding, right? Because with union, we need to think OR and add. So I'm still adding, but now I need to subtract out what I've double counted. And what I've double counted is what's in both groups, which is the intersection. So it's P of A plus P of B minus P of A intersection B. Because that's the intersection right here. So those are our 2 scenarios with unions. They're either mutually exclusive or not mutually exclusive. All right. Now intersection. With unions, you should think OR and add. Intersections, I want you to think and multiply. So see here with these unions we've added. Here, if we're looking for an intersection between 2 events, we need to multiply. All right, so we have independent and dependent events. Independent events means that the outcome of one does not affect the outcome of the other. Dependent, they're dependent on each other. We're going to get more into dependent situations when we get into conditional probability. So, probability of A intersection B is going to be P of A times P of B. Our rule down here, though, our dependent rule, still using multiplication, but now we need to do P of A times P of B given A. Oops, I started to write a G. P of B given A. Given A has occurred. Usually what that means is adjusting the denominator by 1, right? When we did event A, we have a total denominator of possible events, and then if we don't replace the card or replace the marble or do whatever, if there's no replacement, then we need to adjust the total outcomes for event B by 1, by subtracting 1. So that's our 2 scenarios. Multiplication and multiplication, but this is a conditional probability right here. And we're going to talk more about conditional probabilities next class. Just know that you must adjust it for A already happening. Independent events occur with replacement. Dependent occur without replacement. Remember, if I pull a card and then put it back into the deck, my probability of event B happening hasn't changed. So, if A intersection B is equal to A times B, then my events are independent. If it doesn't, then they're dependent. And again, we're going to focus on dependent more next class with conditional probability. I've got 4 more questions for you, just to get some more practice. So go ahead and pause the video and see if you can answer number 1. All right, looking over our scenarios, I think the easiest thing possible is to create a sample space. I either want you to check to see if you can create a sample space or a Venn diagram, because looking at things visually helps a lot. So here we can create a sample space. So we've got 5 members. 2 students will be selected at random. So remember to calculate my total number of outcomes. I've got my first selection times my second selection. So I have 5 students total during my first selection. And my second selection, I have 4 left. This helps me determine my total number of outcomes. That way I don't miss anything in my sample space. All right, so let's see if we can name all 20 of those outcomes. We've got Adam and Bradley, Adam and Carol, Adam and Dave, Adam and Ella. We have Bradley Adam, Bradley Carol, Bradley Dave, and Bradley Ella. Carol Adam, Carol Bradley, Carol Dave, Carol Ella, and then we have Dave Adam, Dave Bradley, Dave Carol, Dave Ella, Alright, so I've got my 20 different possible outcomes. Didn't take me too long. What is the probability that Adam and Ella will be selected? So I'm looking for any of these combinations with an A and an E. It has to have an A and an E in it. There's one. Alright, so I've got AE and EA. So I know I have 2 out of 20, which reduces, if I divide both of the denominator and the numerator by 2, it reduces to 1 over 10. So my answer here is B, 1 over 10. Again, that wasn't the only way to do it. I just like to do visual when possible. Sample space, Venn diagram when possible. Alright, so go ahead and pause the video and try number 2. It looks like a Venn diagram is the best scenario to use here. So I've got 2 events, event A and event B, and it looks like event A and B can happen at the same time. So here's event A, here's event B. Alright, event A and B together is 0.375. So that's my intersection. So automatically I know something about whether or not they're mutually exclusive. It looks like they can happen at the same time, so they're not mutually exclusive. So I can go ahead and eliminate some scenarios. It looks like I'm going to eliminate A and B, because I know they're not mutually exclusive. Alright, our other scenarios are they independent, not independent, or that cannot be determined without the information given? Well, I know my independence rule. If I have 2 independent events, then A intersection B is P of A times P of B. Well, I have the intersection, right? It's 0.375. So let me just see if 0.375 is equal to P of A times P of B. If it is, then I know that they're independent. 0.75 times 0.5. It's going to give me 0.375. So yep, that independent multiplication rule works, so I know they are independent, so C is my answer here. They're not mutually exclusive, but they are independent. Alright, go ahead, pause the video and attempt this one. I hope you realize that this was actually a complement rule problem. So police officers using a radar device, but prior to beginning the speed check, 40% are going to be driving more than 5 miles per hour. So assume that the police officer's estimate is correct. What is the probability that among the 4 randomly selected motorists, the officer will find at least 1 motorist driving more than 5 miles per hour? Alright, so we're going to call event S speeding over 5 miles per hour. So that means we think the probability of event S is his estimate, which is 0.40. 40% of motorists will be speeding, which means driving more than 5 miles per hour over the speed limit. All right. So when we have 4 randomly selected motorists, the officer will find at least one, that word, at least one motorist driving more than 0.5 miles per hour. So the whole reason why it's a complement situation is because the complement of finding at least one is none at all, right? So if I find none at all, then I can do 1 minus the probability of no speeders. That will help me figure out what the probability of finding at least one is. 1 minus no speeders at all in the group of 4. Well, this is my probability of speeding. So my probability of not speeding must be 0.6. 1 minus 0.4. Again, that's a complement rule, right? So if my probability of finding no speeders at all is 0.6, and I've got 4 randomly selected people in my group, I'm going to raise it to the 4th power. So let's go ahead and put this in Desmos and see what we get. All right, so D is our answer. So remember, we can find the probability of no one speeding at all by taking our probability of no speeding and raising it to the 4th power, because I have 4 randomly selected individuals. And the probability that they're all not speeding is multiplication. 0.6 times 0.6 times 0.6 times 0.6. All right, go ahead and try number 4. Okay, here, the distribution of colors of candy in a bag are as follows. So they're not all equally likely outcomes. We've got a sample space here with the different proportions that should add up to 1. If 2 candies are selected at random with replacement, automatically I know if I have with replacement, I have independence, and I can use my independence rule, which is probability of A intersection B is A times B. All right, so it's asking us, what's the probability that they are the same color? All right, so if I'm pulling 2 candies that are the same color, what are my options here? I could have brown, brown, red, red, yellow, yellow, green, green, and orange, orange. So let me calculate all of these probabilities by using my independence multiplication rule. So the probability of drawing brown once is 0.3. The probability of drawing brown twice is 0.3 squared, right? 0.3 times 0.3. Let me go ahead and write it out like that so you can see it, and then I'll add the squared. 0.3 times 0.3, which is the same thing as 0.3 squared. Same with these. Red is going to be 0.2 times 0.2. Same with yellow. And I'm writing it out like this so you can see where I got the squared, the exponent of 2, because we're multiplying a number times itself. All right, let's figure out what these are. Okay, so I got 0.09 for the first one. I've got 0.04, and I can actually just keep repeating that because that's the same for the next 3 colors. And then 0.01. Okay, I've got all these probabilities. Now to figure out what the probability is of drawing all of these, I'm just going to add them up together. I've multiplied because I had blue and blue. But if you look at it big picture, these are my different situations that I could draw to pull the same color. So I could pull blue and blue, or I could pull red and red, or I could pull yellow and yellow, or I could pull green and green, or I could pull orange and orange. That's why I'm adding them up all together here. I had to multiply because my situation was blue and blue, red and red. So you see where the and comes into play with the multiplication, and then adding them up comes into play with the or. So let me go ahead and add these up. 0.09, 0.04, and yes, I could do 0.04 cubed. So when I add them all up together, I get 0.22. So B is my answer here. All right, great work, you guys.